In the previous videos, we first discussed complex numbers and discussed the relation between exponentials and sinusoids, right, in the complex plane. Then we discussed Fourier series and we simplified it into a complex Fourier series, where complex numbers served to simplify the process. But not only did they serve to simplify, they also gave rise to the Fourier Transform, which allows us to parse the frequency contents of a signal. And from the frequency contents, we get an image of the energies at different frequencies for our signal. And now, to build off of that, we're going to talk about Laplace. Now, Laplace was a mathematician and physicist, much like Fourier, and he was also working with differential equations. But his differential equations were not working with purely periodic functions, but rather dampened oscillations, such as one that might look like this, right? Where it's not only some sinusoid, I'll just write a simple sinusoid, right? But it's also some exponential, right? So let's do omega t, and there would be some decay over time or growth, right? But there is this sigma term. And this exponential decay or growth, right, this damping, encouraged Laplace to generalize the Fourier transform, where, if you'll see, the Fourier transform tells us this bit of information, but we have no way of knowing this information. Well, Laplace created a new variable, which is a complex variable, which is a combination of sigma, so the damping factor, plus I omega, or the complex frequency. And this is a complex number. So he placed this into the Fourier integral to give us the Laplace transform, which is as follows, where you integrate over time. It's the same thing as the Fourier transform, except with s instead of I omega, right? Because we've just added a sigma. However, in the previous video, we discussed about a system, right? And we would put in an input, right? We'd put in an input and would get out an output. However, one thing that is important to note about this is the output, right? If I feed in an input at time equals 0, for example, then I should expect an output only after 0. But if I see an output, let's say, before 0 or something, what that means is my system is responding to an input, right, and producing an output before the input is even put in. So we essentially have a machine that gives out an output and then receives the input which produces that output, right? And this clearly breaks the law of causality, which means that there is a clear order to the way things happen. This is a fundamental property of the universe on a macro scale, right? Is that things must obey causality. And if we have a system which has a response that extends past 0 into negative time, we have a time machine. We have an anti-causal system, which does not exist. We do not have time machines. They are not physically realizable, at least as far as we know, right? But with that in mind, most of our signals will be equal to 0 before time is equal to 0. So our Laplace transform can be simplified into this because we are only really going to use it for real systems. Now there is still the original form, but it is now called the bilateral transform rather than the Laplace transform, where the Laplace transform only refers to the positive time integral. Now the Laplace transform is much more useful than the Fourier integral than the Fourier transform for a few things. And one of the main things is, whilst the Fourier transform also has this property, it is much easier to use in the Laplace transform, and that is the Laplace transform of the derivative of a function is equal to s times the Laplace transform of that function minus its initial condition. And likewise, the Laplace transform of a definite integral of a function will produce the Laplace transform of the function divided by s. It takes calculus, it takes limiting operations, right? And it converts them into algebra. And these are called the derivative property and the integral property, and they are extremely useful for differential equations. For example, if I have a differential equation of this form, we can solve this because if we apply this and just replace these, right, and just perform it twice, we would end up with s squared x minus s x of 0 minus x dot of 0 is equal to minus kx. And we can pull this over and we'll get xs squared plus k. And we would end up on the other side with s x naught plus x dot 0. And we would get x is equal to s. All right, now we have turned this differential equation into simple algebra. And now, with the help of a Laplace transform table, we can see that if we get this into a familiar form, we can just read the inverse Laplace transform off that table, because otherwise we'd have to perform complex contour integrals, which are quite difficult to perform in most cases. But to save you the trouble, this will eventually break down into this form, where we have some constant times cosine of omega t plus b sine of omega t. This is the general solution to a harmonic oscillator, and is one of the most important equations in physics, because everything can be represented by a harmonic oscillator. But more importantly to us, this property helps us very much with other differential equations which are used in electrical engineering. Now, to find them, let's first look at a simple DC circuit where we'll have a resistor, right? In this circuit, right, we'll have a voltage signal and we'll have a resistor. Let's say our voltage signal is just a constant, right? So it's just V. Well, what our voltage and current graph would look like, so here we would have the input, which is voltage across time, and we'd have current across time. Well, this would just be constant. They're equal. There is no time variance, right? Now, if instead we put a a resistor and a capacitor, what happens is with a constant voltage, what ends up happening is we have a voltage graph across the capacitor. So our voltage will be measured with this being positive, this being negative. This will look something like this, where it follows an exponential. Now see, this is different to the resistor, where this, if we replace this with just voltage over time, right, what we would find is we would just have a graph that would look like this. So whilst the resistor is uniform throughout time, right, the capacitor has a time varying response, right? Every point in time that I look, I will get a different value. It depends on time. And the same thing is, what if we hook up a capacitor, an inductor, sorry. Well, if we hook up an inductor, what would have is we would have a voltage graph which will look like this, where again we're measuring the voltage like this. It would look like this, where the voltage would drop off. Because at first you'd have a large potential difference, but as it went along, it would just act as a short circuit. Meanwhile, the capacitor would act as a short circuit until, as it went along, it would act as an open circuit. And the voltage would become steady because there is a potential difference across the plates. But now looking further, why do they have these responses? Like looking at the capacitor, if we apply a constant voltage to it, what's happening is electrons are the ones that are moving, and they're actually flowing from negative to positive. So they're flowing like this, and they're being pushed onto this plate, and they're building up. So this plate is becoming negatively charged, and this plate is going to be likewise repelling electrons, or we can also talk about holes, right? And so we can talk about positive charges. So this one will build up a positive charge. And the longer that it is, the more and more it's going to happen. And this is going to set up an electric field, which will hold the other in place. These are attracting each other, right? But now, as we keep it going, eventually they'll get saturated and we'll have the electric field be as saturated as it can be, right? But then as soon as we cut off power, what happens is the electric field wants to break, because all of these charges that are close together don't want to be close together. So if there is a path to close these, it will flow. And it will balance out the imbalance across the plates. Right? So the electric field is actually what causes this time varying response. Right? And with the inductor, an even more interesting story plays out, where if we apply a voltage, we have electrons coming through. Right, so electrons are coming here and they're flowing around the wire. And according to Ampere's law, these electrons flowing, because they are moving charges, they will generate a magnetic field. And the magnetic field will be around the wire. And this magnetic field, because these coils of wire are so close to each other, will cut through the other coils of wire, right? And what will happen is, according to the Lorentz Law, which is as follows, if there is relative motion between a charged particle and a magnetic field, there will be a force acting perpendicular to both of those vectors. And the effect of that is we are going to induce a force on some electrons inside of the coils, and these electrons are going to be forced in the opposite direction to which the electrons are coming from. So there will be a pushback by the inductor. It's almost like the inductor is refusing to change the current going through it. But as time goes on, the force pushing back decreases and decreases, and eventually the current going through it saturates. And when this happens, a large magnetic field is set up in the inductor, right? And it essentially acts as one big magnet. But whilst it acts like this magnet, if I increase the current, right, past a certain level, this inductor will get saturated, and in this space, there will be no more space to produce any more magnetic field. So the more current I add past a certain point, there will be no real effect or change on the magnetic field it produces. However, if we now reduce or completely get rid of the voltage being applied, what happens is, even though there's no outward electromotive force, right, pushing these electrons along, there's still the magnetomotive force of this magnetic field that is pushing electrons out, right? It still has the memory. The magnetic field is still there, and it takes time to dissipate. And whilst it pushes charges out, the net charge flowing through it starts to decrease, and thus the magnetic field slowly starts to decrease, and eventually it will become stationary. And it will stop. Now this time-varying response, right, also comes, instead of from the electric field, this time it came from the magnetic field. Energy was stored in the magnetic field almost, and that magnetic field that was being set up opposed the change. It opposed the incoming current, and because of that, it created a time-varying response. And in fact, we can write the equations relating voltage across a capacitor and current as follows, where it is the integral from 0 till some time of current with respect to time. And for an inductor, it is the inductance times the time derivative of current. Now we see that the time-varying response is represented by calculus, by a derivative and an integral, because the time-varying response is opposite. Whilst the capacitor acts as a closed circuit and then becomes an open circuit, the inductor acts as an open circuit and then acts as a closed circuit. Despite all of that, if we make a circuit like this, where we add a resistor, an inductor, and a capacitor, right, all in series, we have what is known as a series RLC circuit. And in this, we will have a differential equation where the voltage across this will just be current times resistance. But here we have that it is a derivative, and then here we have an integral. It becomes quite difficult to solve, and especially if we have a signal such as mains voltage, which is varying 50 or 60 times per second, right? And might even have a DC component and might even have fluctuations on top of that. It becomes very difficult to solve these equations purely through differential equations in the time domain. But that's the thing. It's difficult in the time domain. We don't have to work in the time domain. We can just take these properties of the Laplace transform and move this into the Laplace domain. And when we do that, well, this is an integral, so it becomes 1 over SC times I, and this becomes SL times I. And if we now take the voltage and divide it by the current, we get the relationship between the input and the output. Or rather, we get the transfer function, which is normally represented by an H or a G, right? But in more specific terms to electrical engineering, we get the impedance, right? And the impedance of the circuit is equal to, in general, we have resistance, which has no differential or integral components, which means it has no time varying response, which means it does not have any electric or magnetic effects. It is just a straight heating element. And then we have SL plus 1 over SC. Okay. However, for most signals that we deal with, especially in alternating current, hence the name, this S is equal to 0 plus I omega, right? There isn't really a dampened component, it's a pure sinusoid. But also, in addition to that, this I, the square root of -1, right? We're already using I for current. So what we're going to do is we're going to replace I now with J. J is the same, and J is just the square root of -1, right? It is the same, just a different letter, because we don't want to have any overlapping symbols. Now, with this change in mind, let's substitute in S for J omega, and we end up with R plus J omega L plus 1 over J omega C. Okay, well, we remember that 1 over a complex number, right, is just equal to minus that complex number. So now we can just factor it out, so we find that the impedance of a circuit is just R plus J times omega L plus 1 over omega C. Or we can even further factor this into just saying that X is reactance, where reactance is a measure of the time varying response, or rather it's the measure of how much capacitance and inductance are factored in. Now, one very important thing to note is that the inductance varies with frequency directly, whilst capacitance actually decreases with increased frequency. So let's take a look at why that is. If we look at the capacitor, right? If we apply a voltage, what happens is some current builds on, some charges build on the plate, right? But it mostly acts as an open circuit. But if we switch directions in time, it will discharge those charges, and then it will start building on the other plate, and then we change the direction again, and we don't let any charge actually, or any significant charge, build up on the plates. And what happens is it essentially acts as an open circuit to high frequencies. But for lower frequencies, the capacitance has a more impeding effect on the current. And in fact, at the limit to DC, you'll see that if you substitute omega for 0, you will get infinite impedance for the capacitor, or rather, it acts as an open circuit. But inductance to a DC input will just act as a short circuit. Of course, in the steady state, not immediately. And now we can finally look at a power triangle to really have an overview of what all of this means. Well, the power we normally are used to is real power. This power is used for heating, it's used for running lights, it's used for running your computer, it's used for most things that we would consider useful. And this is called real power. But there's also what is called reactive power. This reactive power is a measure, like I said, it's a measure of the electric and magnetic fields, right? Of the power going into the electric and magnetic fields. But even more importantly, because the response of the components changes with respect to time and with frequency, what reactive power really tells us is the degree of time-varying response, or rather, how much the energy is being spread out over time. The energy that goes into an inductor is not immediately dissipated, it is rather stored in the magnetic field, and likewise with the capacitor, it's stored in the electric field. The combination of real and reactive power is known as apparent power. This is the value that you will read is being drawn at the source. This is the total amount of power that you are drawing, but you'll only ever see the effects of real power. So from a physics perspective, the existence of complex numbers in circuitry, especially AC circuitry, tells us that there is a certain frequency-dependent, or rather time-dependent response, which is caused by energy being stored in electric or magnetic fields. However, in a mathematical sense, the reason why these complex numbers are here are simply because we had differential equations, and these differential equations were difficult to solve through calculus, so rather we just transformed them into the S domain, where rather than being a differential equation, it is just a standard algebraic equation.